My name is Walter Zemsky. If you didn't already know that, you probably already know that already. I'm a pilot for FedEx, so I fly for CSA, and CSA is contracted by FedEx to fly FedEx cargo and FedEx airplanes, so I just fly FedEx airplanes hired by CSA. I also instruct part-time at Legacy, and been doing that for a year and a half, 3 years? 2 years, something like that. Drzemski is my last name. That is Polish, if you're wondering. My dad was adopted though, so I inherited the name. I did not earn the name. So along with my red hair, I get the ginger jokes and I get the Polak jokes. So I've been the subject of workplace harassment since before it became cool. But I'm kidding, obviously. But so yeah, again, appreciate you all coming. As a Christian, I've enjoyed watching the weather, and it's a God-designed phenomenon, obviously, along with the rest of His creation. But it's really cool to see His design from the perspective of in-flight. Hey, Mark.
Of inside of it.
Of inside of it, yeah. Yep. So that's kind of why I enjoy the subject and why I enjoy it. As I said, it's designed intelligently designed by God, and it keeps us alive for most of the time and comfortable around here for about 30% of the time. Purpose of this seminar is we're going to go through this Aviation Motor Advisory Circular, kind of pick out the fun stuff in there. There's a lot of dry stuff in there. We'll pick out the fun stuff, and it's mostly to give you kind of an upcoming knowledge of, knowledge test or written test or a check ride, kind of just a general overview of the weather theory. And that way, when you study it on the ground, you'll think, oh, I heard that. Not necessarily, you don't need to take away a lot of information. You just need to kind of have it in the back of your mind for when you come across it again. So that's kind of the purpose of this shindig here. As I said, we're going to go through the advisory circular. We're going to see a lot of diagrams that are probably going to be familiar when you're doing training, because a lot of training materials take their information from this document. It's a FAA document distributed by the government, so it's politically correct. But you'll see it's not regulatory in nature, it's just advisory. It just has a lot of information, but it's good information, and it is informative. So it's kind of where all the other aviation training handbooks get their source material from, if you will. If it gets dry, feel free to fall asleep, because that way I know I'm not doing my job. If you try to keep your eyes open, I won't know if it's not entertaining enough. So we'll just kind of skim through this and pick and choose what we want to go through. Just kind of all the main material. That's an intimidating table of contents. But
What was the date on this release?
this
2016.
Whoops. Maybe lose my spot.
That's all it's good.
That's all it took. I just had to click on it.
Do you find
Okay.
this out on the FAA website?
This would be on the FAA website. It's also, if you just do a Google search for the FAA Aviation Weather Handbook, it should be the top thing. But it'll have the FAA website listed as the URL. So it'll be one of your first search results, but it'll have the FAA URL there. So it'll direct you to the right spot. So chapter 1 is called the Earth's atmosphere. Mainly the two things I wanted to pull out up here is that it's mostly composed of nitrogen, and then oxygen is about 20%, and then all the rest of the things are like the last remaining 2%, something like that. Not much. It's mostly just oxygen and nitrogen. So that'll be on the written test. They might ask you a question on what's the atmosphere composed of. You don't need a really solid knowledge of the exact number, but just the fact that it's mostly composed of nitrogen and oxygen, and then a bunch of other random little gases. This is a good diagram for the vertical structure of the atmosphere. We have the troposphere down at the bottom, that thin little layer. Most of the atmosphere is in the troposphere, and the temperature decreases as you go up. So that's what that yellow line represents, is the temperature. So it decreases as you go up. The tropopause is where it stops decreasing, and it stays the same as you go up. And then we have the stratosphere, it starts warming up as you go up, and then the stratopause and mesosphere starts cooling down again, and the troposphere. So what happens here is that right down here it's kind of unstable. It has a tendency sometimes to be unstable, so we get thunderstorms because the temperature decreases as you go up and all that sort of stuff. But that also means that since it stops decreasing right here, you get a cap on how high up a thunderstorm can go. So if it's another way that the atmosphere is designed by God to keep us from having insane thunderstorms that would destroy the earth, is they only go up this far. So that's kind of an interesting how it goes back and forth, but it stops right there where we have our maximum thunderstorm limit. And it's designed that way. All right. I think that's all they wanted to really pull out for that section. Heat and temperature will be the next one. I think I missed it. Yeah, there we go. Okay. So every weather phenomenon, and you'll get this on the written test. So I'll ask you, what's the beginning of all weather?
Unstable atmosphere.
Heat transfer.
Heat transfer.
Heat transfer. There we go. It's the uneven heating of the Earth's atmosphere and how that interacts with, you have warm air in this spot and cold air in this spot. This air is more buoyant and it mixes around, goes up, goes down. That's what kind of makes the weather. And it heats up more towards the equator, of course, since that's where we get our direct sunlight. And it's cooler towards the poles, obviously. Different types of heat transfer. This is also a good one. Heat can be transferred, obviously. We talked about when the atmosphere is mixing together, that's called convection. So convection is just when you have a cup of coffee and you pour cold water into it. That's convection. Conduction is if you have something touching. That's, you're absorbing heat or releasing heat. That's conduction. And radiation is if you're standing in front of the projector and you're feeling the heat off of it. That's radiation. So we get radiation off of the sun. And that's those three ways of moving heat around are kind of how everything works. And this is they call this the solar zenith angle, of course. This is what I was talking about with being cooler at the poles and warmer towards the equators because the sun hits the equator more directly. Pretty simple stuff. That's it for one more heat and temperature thing. This is a cool diagram here. Water absorbs heat and releases heat much slower than anything else. So sand will absorb heat a lot quicker, so it warms up fast, and it also releases heat really fast. So anything solid will do that pretty much, but water has a lot of what they call thermal inertia. So once you get it warmed up, it doesn't want to cool down, and it's also really hard to heat up. You just ask your hot water bill. It's tough, but that also means that once you have inserted energy into a weather system with warm water, you can have some excitement on your hands. So that's kind of the things for the heat and temperature. Water vapor is the next one, and this is a hydrologic cycle. Say that word correctly. You can't really see the words on here, but it's some pretty easy terms. Precipitation, obviously, precipitation is evaporation. Condensation is when it turns into when invisible water vapor turns into visible water droplets, clouds, stuff like that. And then some other things you have. Deposition would be water vapor going in directly to ice, like on a surface, and then you have transpiration, which is off the plants, stuff like that. They probably won't give you too many questions like this on a written test. Definitely not on a knowledge test or on a oral test. But just some good terms to have in mind, because you'll run across them and you'll want to know what they are. So here's all the terms here: transportation, precipitation, runoff, all that fun stuff. Another thing, let's see more on more on water. Here we go. Here's a good diagram on humidity. So the principle here is that the warmer a parcel of air is, the more water it can hold. So if you warm air up, you can suck water off of a moist surface or something like that. So if you have a warm body of water, it'll warm the air up, and then it'll suck water off that body of water, and then it'll move on to some other area where it'll cool the air back down usually, and then it can't hold the water anymore, it goes into a cloud, and you get advection fog. But we'll talk about that more later. Principle here is warm air can hold more water than cold air. So if you cool it down, eventually it gets to the point where it cannot hold any more water, and you get what's called saturation. And saturation is when you have clouds, rain, precip, snow, whatever, it's starting to deposit the water into little globules instead of being invisible water moisture. So that's what the dew point is. The dew point is the point at which you have to cool the air down to form condensation. What else did I want to bring up with that? Phase change. Phase changes are fun. A phase change is when you have solid to liquid, liquid to gas, stuff like that. The terms you might not have heard are sublimation and deposition, which is vapor to solid, and the sublimation is solid to vapor. So like ice to directly water vapor. The other main thing you want to get off of this is that whenever you have a phase change, you have a release or an absorption of heat called latent heat. So like you have to make your pot of water hot before it boils. That's a latent heat transfer. When the water turns to steam, it requires heat to be poured into that pot of water. So how this applies to weather is if you have a liquid turning to vapor, or you have a vapor turning to liquid, you're going to also have that parcel of air either warm up or cool down based on what type of phase change you have happening inside that parcel of air. And that's called your latent heat transfer. So that'll be another written test question. What is that type of heat transfer called? That's kind of it for number 3. Earth atmosphere heat imbalances. Not much on this one, but this is kind of the main document I wanted to show, or the main graph. The principle is that the incoming radiation from the sun, because that's our main source of radiation, obviously, gets absorbed into the Earth's surface, and then the Earth radiates it back out. And what will happen a lot of times is it'll either get everything that happens in the atmosphere kind of interferes with that. But in the end, it all stays exactly the same. So whether there's clouds that are reflecting it back in, or whether clouds reflect it back off into the atmosphere, or if it's absorbed by clouds, or if it's absorbed by dust and particulates in the atmosphere, there's an equal intake and outflow of radiation in the Earth. It's just another aspect of how this is a designed process. It didn't happen by accident. This is a God-designed principle. It's exact. It doesn't. We haven't exploded. It's been 6,000 years of this happening. Yeah, right. So this is another example of it's a greenhouse effect with water vapor. So if you have, or I should say, clouds, because water vapor will just kind of go through it. But if you have a cloud, it'll kind of reflect the heat back towards the surface of the Earth, and it'll kind of trap the heat inside. So what happens at night, in this case, is it'll radiate the heat. The Earth will radiate the heat back towards back outside of the Earth, and since there's no clouds stopping it, it'll cool down really, really fast. And what happens a lot of times there is that you'll have radiation fog, and we get that occasionally if in spring and fall, usually when you have high moisture contents and just rapidly fluctuating temperatures over the course of a week. There's one week I think it was like it was like 15 degrees and then 70 degrees or something like that. It was some way crazy temperature swing we had in the course of a week.
So radiation fog as opposed to advection fog, radiation fog is just the thing that happens like in the morning.
Correct. Yep,
Just
that's a
because
good
the
point.
temperature
That's a good
happened
point.
to
Yep,
the bingo
yep, overnight.
overnight.
Yep. So, yeah, radiation fog is a very short-term phenomenon as opposed to something like advection fog where you could have it for
Like San Francisco.
a couple days. Yeah, San Francisco, yep.
That's their weather
Yeah.
They have a name for it, I think. I think it's George or something.
George. Keep George out of the area. This is a pretty simple principle development of thermal, but just the when you have hot air warming up at the surface, it's more buoyant than the air around it, and then it'll go up and kind of look like that balloon.
Basically,
Yeah, looks like lava.
I think it's kind of the same thing, right?
now.
Pretty much, yeah. And when you fly through, you'll feel it.
Yeah.
It'll feel like lava.
Been their experience. That.
Yeah, I'm sure. Have you done a lot of have you done winter flying much, or mostly just summer flying?
I started last September.
Okay.
We went into December, then January and February, and the winter wasn't my friend.
Mm-hmm.
Didn't get up as much as we wanted to.
Yeah, winter you have low clouds, and in summer you have thermals and wind. Spring and fall you have wind. Oh, there is always wind. Yeah, it doesn't matter what time of year, does it? There's just always wind around here.
Troy and I, we were going to do a solo, and the weather was great. You could see the sunshine. It was beautiful.
Mm-hmm.
You got up and there was no horizon. It was gone.
It was just that hazy, or were there?
Just that hazy.
Yeah. Huh. So this is, I think this is chapter 4, something like that. But this is the altimetry and pressure section. We'll probably, there's some of these we'll kind of breeze through, and you'll come back for another weather seminar, right? And get the end of the story on some of these areas, because it more applies to flight planning purposes and stuff like that. But the pressure is kind of interesting. There's a couple different ways to measure it. For one thing, so you have PSI, which is 14.7 at sea level on a standard day. 2992, you've probably heard of that quite a bit. 1013.2 is your British way of doing it, which makes more sense in my opinion. But 1013.2 millibars is kind of the other, is kind of the international standard way of doing altimeter stuff. So if you ever fly internationally, they'll probably still be altimeters, but mainly you might get that question on the written test too. What's the standard atmospheric pressure at sea level in millibars? And you'll go, oh, come on, why? Why that question? But 1013.2 millibars. Also, some other fun facts about the altimetry stuff is that the pressure will decrease about 1 inch per 1,000 feet, roughly, sort of, kind of. The atmosphere is actually squeezed a little bit towards the poles, and it's a little bit wider towards the equator because of centrifugal force. And centrifugal force isn't a thing, I know, but it's wider at the equator, so the further up you go, well, it's just the pressure levels are spread further apart. Whereas with what am I trying to say? The poles, it's squeezed together a little bit more. So you might not be as high as you think you are, but your altimeter says it is. That makes sense. Kind of the same thing with warm and cold air. So cold air is very dense, warm air is very spread apart. So if you have, I kind of skipped ahead, but here, if you have a warm parcel of air, it's very spread apart, cold air is very dense. So the same principle applies. Your altimeter might say, you know, in the cold air I'm flying right here, I am at 10,000 feet. And your altimeter will say, here on the warm air, I'm also flying at 10,000 feet, because I have the same amount of pressure beneath me, if that makes sense. But that's not true. That's 10,000 feet, right? So that's kind of the temperature effects on pressure that'll affect your altimeter. And we actually don't have a way to correct for that. You can correct for pressure, but your altimeter is just incorrect sometimes when it's very cold or very warm, and you just deal with it. If you're flying on instruments, there's some, like, on some approach charts at high altitude areas that have a temperature limit. So if it's below a certain temperature, you cannot fly that approach. And that's why is because if it's cold enough, you're going to be a lot lower than what you think you are.
Oh.
Where would a temperature, would it be listed on the approach plate?
It's listed on the top left corner in the notes section. So you have your non-standard alternate minimums, takeoff minimums, temperature limitation.
There's a place in the fine print where it's really, really hard to find.
Yeah,
Small.
yep, the small print.
He'll never use this.
Batteries
It's
not
like,
included.
oh
some
yes, you can't
restrictions
do this
apply.
approach, it's too cold.
Oops.
So here's another interesting little picture here. 400 millibars, talked about millibars in altimeter settings, 400 millibars is equal to 24,000 feet. And why is that important? Well, on some of these weather charts, and we aren't going to get too deep into weather charts, but this is what they call a significant weather prognostic chart. And this could be a written test question, but this is valid from the surface to 24,000 feet or 400 millibars. And they won't say 24,000 feet, they'll say 400 millibars right here in the corner. Low level surface to 400 millibars. Because they assume pilots know what millibars are. Around here, why do you need millibars? We have altimeter settings and feet and all that sort of stuff. But so that might, the only one I can think of is 400 millibars. That's the only millibar in 1013.2. Those are the only 2 millibar values that I've ever used. Also, pressurized air. We talked about warm air. If you pressurize air, it'll also do some weird things. So if you pressurize a parcel of air, it will warm up, right? Because you pressurize stuff. If you work with pressure or anything like that, you'll know that. Also, if you suck air apart, or if you decrease the pressure of the air mass, it'll cool down, conversely. And that's just because it takes energy to compress and expand air. And it, as the air is interacting with itself on a smaller scale, that's just a byproduct of that. Where that comes into play is if you have like a descending air mass. Descending air mass is constantly getting pressurized, so it'll become warm, and a rising air mass will become cooler as it rises. And that's called adiabatic cooling or warming. We'll get to that in a minute, but we're going to come across that term. Again, also, air with water vapor is less dense than air without water vapor. And that's just because water vapor, the water molecule is less dense than the nitrogen molecule, I guess. My brother could tell you the atomic characteristics of both of those things. But
One has hydrogen, right?
water has hydrogen, and hydrogen is heavy, right? Or no, it's
Really
light, it's
light.
very, very light, that's light. Yep, so hydrogen and 2 oxygen molecules as opposed to 2 oxygen molecules and nitrogen, whatever that is. But hydrogen's really light, so that must be why
It's
it's
just fertilizer basically.
it's fertilizer. Yeah, yep. So that's where's I going with that? When you're talking about density altitude, when you have a high moisture content, that's why it's a worse thing for your airplanes, because the air is just not as thick. And it's not a significant variable, but it is a variable, and they might ask you about it. I don't know. Water vapor, not a good thing. Plus, your engine can't consume it, so well, it doesn't work with it. It can't burn water. So, associated with pressure, these are all really complicated. Here's a formula. Equations. If you like equations, feel free to research that.
I've seen that before.
Yeah. I had to do an aviation aerodynamics course
Ooh, that's cool.
last fall, and we had a couple of those.
A lot of this stuff I've seen in heat transfer when I was in my college courses.
Yes, yep.
A lot of this stuff is a similar stuff we do.
Mm-hmm. Yeah, it applies across a wide range. Here's another helpful diagram. It shows you that the pressure levels might not stay at the same altitude wherever you're going. So this is a high pressure area, and this is a low pressure area, I believe. Yes. So when you have, like, let's say, pressure altitude, what's pressure altitude? It's the height above the standard datum plane. What does that mean? Well, the standard datum plane is wherever 2992 is. So 2992 could be at sea level, right here, or it could be right here, 1,000 feet above the surface. So when your airplane is measuring the distance between and the standard datum plane, you're going to be at a lower pressure altitude here and a higher pressure altitude here, if that makes sense. So that is what your pressure altitude is. I don't know if that would go well. You just screw your 2992 into your altimeter and it subtracts how much distance you are from that pressure level, and that's your pressure altitude. Kind of something they don't teach you when they just give you the
They
definition.
have weather charts that are, there's something called heights. Which is
Okay.
exactly, it's like how high is
How high is
fill
the
in the
pressure
blank,
level?
yeah, what pressure you're looking at.
That's interesting.
And it just, because, it's how much atmosphere is above you,
Yeah.
essentially.
Yep. And your altimeter kind of does the same thing. It takes whatever pressure you're at right now, it subtracts whatever pressure you have in the window there, finds the difference, and then multiplies it by 1,000, you get your feet. And that's really all it does. And you can do that by hand on a piece of paper. It's really cool when you know what you're. Of course, then you have to know what pressure you're at right then, so you have to screw your altimeter all the way down to 0, and then look at your pressure in the window and screw it back to whatever this pressure is at your destination airport. Find the difference, multiply it out, and then you could either read it on the altimeter in 2 seconds, or you could figure it out with your pencil in 5 minutes. But it's kind of cool all the same. Sweet. That's the pressure altitude. We're kind of skipping ahead here, but that's fine. Just have to scroll faster. The other types of altitude that you might run across are true altitude. Actually, no, I'm not there yet. I missed it. I'll just talk about it here. True altitude, which is your actual height above the surface, and your indicated altitude, which is whatever you see on your altimeter, which could be wrong if you have the wrong pressure setting in there. And then finally, density altitude is whatever altitude your airplane wants to perform at. So if you have a really hot, so not dense, low pressure, not dense, and high humidity, not dense, so all those combined will give you a high density altitude. And it's a weird term because your mind wants to say high density and then altitude, but it's actually, you should think of it as high altitude density. If you think of it as high altitude density, it clicks a little better. The density is an adjective modifying altitude. If you have a high density altitude, it's just stating what altitude your airplane wants to perform at. So high density altitudes are not good when it comes to aviation. Conversely, you get really low density altitudes in the winter. You could have below sea level density altitude here just because it's that cold. Surface analysis charts are a lot of fun. These are kind of my favorite things to talk about. And you'll find these on the written test, and if you ever take a check ride with Jordan Hall, our DPE, one of our owners, fantastic guy, he loves to talk about these too, so we get along really well on check ride, because we both like to talk about these things. But you kind of have to break it apart a little bit. You have frontal systems, and you have pressure systems that are shown on these things. So we'll talk about pressure systems right now, and we'll move on to frontal systems later because they're a different topic. But low pressure, obviously, high pressure, and then these lines in between are the lines of equal barometric pressure. They're called isobars, isobarometric lines. Iso meaning equal, baro meaning barometric. They're all labeled with their barometric values. So this one is the 1,000 millibar level. And that's just an equal, so it's like a topographical map. You can look at the high pressures as the mountains and the low pressures as the ridges. And then if you've ever looked at a topographical map, I guess you kind of have the idea here. But if the lines are spaced far apart, that means that there's not much of a pressure difference. If that makes sense. So it's decreasing very slowly. If they're very close together, like up here, that means you have a very steep pressure gradient, very windy, because there's a lot of what they call pressure gradient force. We'll talk about that when we get to wind. Actually, that's the next topic. Never mind. But when you have the pressure levels very close together, that just means that you have a steep hill, and so that the wind's going to flow faster down the hill towards the low pressure. So that's kind of the. I don't think I want to bring up anymore because we're going to talk about that. Yeah, that's. I think that's a. Is that a tropical? That is a hurricane, isn't it, Thomas?
Oh, I don't know, what's the usual, I'm not familiar with the pressure levels.
With the pressure values for
It
hurricanes.
doesn't look steep enough.
Yeah, it looks like it's already crossed Florida or something like that.
Yeah. What time of year is it? May? It's too early.
Okay.
Just your average sort of low.
Of course, then you
Is that
also
a
have
high? Is that a
tropical
high?
depression, yeah, because they also have those. That's a high right here. That's a low right there.
So those numbers, that's on the surface elevation?
That is on the. Those are on the millibar values
At the
the
surface?
surface. Yep. At a theoretical sea level surface. So these 1024s, let's say, or let's say 1020 right here. So that goes, all the way up here to the coast. That goes all the way here into the Rocky Mountains. I believe that's the sea level.
Would make sense.
Yeah, millibar value. I'm probably wrong on that. It would make sense. It would make more sense, I think, because you have your weather measuring systems that are actually reading off these values. So that would make more sense if it's the surface surface chart. So I misspoke there. So those are most likely the surface
And
values.
down in the left-hand corner, it says surface analysis.
Surface analysis chart, right? Yeah,
So it'd be surface.
I stand corrected. Alrighty. Let's talk about wind, because wind's fun. We're just talking about this. Pressure gradient force is just, these are, here's your lines of equal barometric pressure. If they're close together, you have a stronger pressure gradient force and a stronger, higher wind, if that makes sense. So it just means that the stronger the pressure gradient force is, the more wind you get. Also, yes.
Go back up to that.
Yes.
So it goes from high to low?
Goes
That's
from
the
high to low,
direction
yes.
your wind is.
Yep, yep. Sort of, kind
Sort of a roundabout way.
of. Yeah, yep. So the other force acting on the wind is the Coriolis force. The Coriolis force is just the fact that you have, a spinning disk right here. If you start in the middle and try to move your pencil to the outside, you're going to come up with a curved line. And since we're spinning on a sphere, if you start at the equator and go toward the poles, you're going to have conservation of momentum, and your wind will be deflected to the right in the northern hemisphere. If you're in the southern hemisphere, it's backwards, so we won't worry about that. But in the northern hemisphere,
It's a flat earth.
yeah, you're right.
I knew it. I knew it.
Flat Earth theory. So if you start at the pole and go toward the equator, it'll deflect to the right. If you start at the equator and go to the pole, it'll deflect to the right. So no matter which direction you're going, it'll go to the right. Whereas at the same time, the low pressure will pull you to the left as you try to go toward the pole. So eventually, as you try to go toward the low pressure area, eventually what will happen is you will those forces will equalize, the pressure gradient force and the Coriolis effect, and it'll kind of end up orbiting around a high pressure or a low pressure system. Same thing as orbital mechanics, really. If you have the space station has an equal centrifugal force going this way and gravity force going this way. Same thing with the low pressure and high pressure systems. At the surface, you have more of a direct flow from high to low pressure because of the friction force will kind of cancel it out. So if you have, you have this model of explaining things, which is true at higher altitudes, but when you get down to the surface, it'll probably aim a little bit more towards your low pressure. So instead of going right around the pressure areas, it'll kind of aim a little bit more towards that high to low pressure, just because of the friction force. And here's kind of that diagram explaining that, I haven't wrapped my head around that yet. Fun fact is that the jet stream happens because of Coriolis force. Just how as wind at the equator moves towards the poles, you kind of get that conservation of momentum, and you get a lot of high-speed wind aloft. Here's one model of explaining how heat is circulated and all that sort of stuff, and then here's another model, a little more complicated, and that's just kind of as they figured it out over the years, they come up with different models of explaining things. And there's always exceptions to this, of course. You could have some sort of, this might be a little narrower, that might be a little wider, you could have a cyclone messing with stuff, or whatever. But roughly, that's how it looks.
I got a question.
Yes.
Are the prevailing winds north of the equator different than south of the equator, based on that?
I
Like
would
if you're
guess,
sailing across the
yeah.
world or something, or flying or whatnot.
Yep, I would guess so.
I hadn't thought about that.
Depends on the time of year,
Yeah,
Sure.
right? You have the trade winds, as they're called, and then
sure, yeah, yeah.
certain other times it's, you know, it varies on how high you are,
Mhm.
or your latitude.
Kind of like toilets go one way
Yeah.
on one side of the equator. Same thing with wind then, probably?
Well, toilets will actually, there's a video online of this, toilets will flush whichever way they want to.
Really?
Yeah, yep. If you take a big swimming pool though, and you set it in your garage and let it sit for 3 days, and then pull the plug on the bottom, and then watch it go, you'll see a very, very, very small amount of vortice action. But with a toilet, they just kind of aim the jets one direction, and that's just kind of how it goes.
Oh.
But yeah, essentially, the cyclones go the opposite way down south.
Correct. Yeah. Yep. So, but that is true. It's backwards
I
down
hadn't thought
south.
about that.
Yep. And you will be able to see that phenomenon in a swimming pool if you let it sit for a couple days. But toilets are just they're much faster, and they're not designed that way. Yeah.
They have something pouring into it. And that's what
Yeah.
they-
Yep. They're biased.
They're probably flushing bias.
Biased toilets. How do we get on this topic?
Sorry.
No, I appreciate it. It's fun. There's a lot of stuff here that local ones. We'll go over those. This kind of goes back to the the surface heats up faster in some areas than others, and more specifically, land heats up faster and cools down faster than water does. So if you have a lake next to land, it'll heat up at different rates. If you have a cool surface, you'll have descending dense cool air. A warm surface, you have the other way. So you have wind going this direction of the surface towards the warm area, and then a lofty kind of the other effect. But that's kind of how you get different types of land versus sea breezes, mountain versus valley breezes. So here's a land breeze, or a sea breeze, sorry. Happens in the afternoon when you have intense heating of the surface here, and then of course the water wants to hold its temperature from last night, so it's not warming up as quick. What will happen there is that you get warm air here, rising, descending towards the cold air over here, and then it is drawn over towards the thermals that are happening in this direction. Exact backwards thing happens at night. Here's another daytime example. What'll happen sometimes is if it's strong enough, you'll get this sea breeze front type of deal, kind of a miniature front type of thing, and you'll get some cumulus clouds, cool little effect.
Or thunderstorms.
Or yeah, thunder, because it's a lifting force, so you could get thunderstorms off of that if you have the right conditions. And we'll talk about those in a minute because I like thunderstorms. Land breeze, of course, as I said, happens at night. Just the exact backwards effect. Lake breeze, you could have clouds on either side of the lake, just because it's it kind of accumulates on on both sides. This is a really cool picture. I think is that Lake Superior or something like that. But it's just absolutely dead out there because you have descending air. It's warming up. It's compressing. It's able to hold a lot of water, and then you have rising air around the around the outside, and it's already warm, and it's picked up some water, and it's rising, and it's cooling off. So that's where all the condensation is happening. Valley breeze happens the same way. Valley breezes are kind of tough to describe, I guess, because it's the whole surface of the valley that's heating up. And as it heats up, the air kind of goes up the sides of the valley, and the air above the valley descends down the middle and then goes up the sides. Kind of the backwards effect again happens at night. So you have this effect at night where air kind of goes down the sides of the mountain and then rises in the middle. But that's kind of a weird weather phenomenon that I haven't experienced because I haven't flown the mountains. I want to do it sometime. But you might be a little irritated by getting that question on a written test because you never had to deal with this, and then they're asking about it. But it's a good point to make, I think. What's next? Air masses. Air masses are classified based on their temperature and their moisture, and that's really all you need to know. Just kind of depends on where they're at. So an air mass in Alaska is going to have a different, temperature and a different water content than air in over Arizona, something like that. It all kind of depends on where it's at. And then if you have two air masses competing with space over each other, you get one taking over the other, and then you get fronts and stuff like that. So we'll kind of try to breeze through here quick. Types of fronts. So these are the different types of fronts. You have cold fronts, which is a cold air mass taking over a warm air mass. Warm front, warmer mass climbing on top of a cold air mass. Stationary front, where neither of them are really moving around a whole lot. And then a occluded front is when a cold front actually overtakes a warm air mass, a warm front. So cold front overtakes a warm front and slides underneath both air masses at once. And that's when you get a lot of excitement. It usually happens around a low pressure system. That's kind of some diagrams on that, but you'll see those later when you're doing your training. Here's kind of the wave cyclone model, which is interesting. So you have a stationary front, and then wind going two different directions. And then if you happen to put the low pressure system right in the middle there, it'll start to rotate. When it starts rotating, you have the cold air mass up here start to overtake the warm air mass down here, as you can see in this case. Cold front and a warm front. As that develops, it'll get more and more pronounced until that cold front, since they move faster, it starts to overtake the warm front. And then you get your occluded front kind of at the top of the low pressure system here. And as it kind of moves this direction, it'll deposit all its stuff back here. So you get kind of a moderate warm front, and then an intense cold front, and then just everything left over on the back side of the low pressure area. Makes a mess. And then you have to fly through it, of course, or not. Yeah. Depending on who you fly for. What types of airplanes you fly.
Classic triple point.
Yeah, so this is a cool little diagram here. This is called a dry line. Usually dry lines don't exist except down in Texas, Oklahoma, because, in my opinion, I think the Rocky Mountains kind of hold back the moist and the dry air up more to the north, but down here they are free to mingle with each other. And what happens, or they don't, you have a dry line separating them. But what can happen there is you have the potential for exciting weather, thunderstorms, stuff like that. And I don't know why exactly, but it's just the intense reaction between the dry air and the moist air. I'm explaining that.
It's essentially like a dry line can operate in the same way as a
front.
As a front. It's basically a front.
Yep.
So
the moisture would be lighter, I would imagine, right? So it kind of operates in that regard. The dry air would slide underneath the moist air.
right, and so
Okay.
it pumps it up, and this is typical like storm chasing chart in Oklahoma,
Yeah.
Texas.
You want to be here.
Yeah, you look, they call it the triple point, where it all sort of matches together. They're not really matching. It's way up there in Kansas. But
yep.
Yeah.
But you get a lot of excitement right there on
And
that.
the dry line goes forward during the day and then recedes at night.
Correct, yeah, yep. So that's another thing, it kind of moves this direction as the dry air heads this way, and then it comes back. Just because the Rocky Mountains are always there, all the time, but they're not here down here. So it's kind of a weird front, and then it kind of stays in the same area and just kind of moves this way in the daytime, back in the nighttime, and then it's just there.
So it's always a dry line?
Pretty much. Sometimes it's not
more
there.
pronounced, yeah.
And sometimes it'll make its way all the way up to Kansas or Nebraska. Like I think a couple days ago I was in South Dakota almost. But usually it just kind of stays down here as a little section, and you can't really see it all that well.
Is that put on any charts?
That's put on your surface analysis charts.
You can also see it on satellite. There's all of a sudden no clouds.
Okay.
Yeah, and in this case, there'd probably be what they call cloud streets in the moist air section, so they're moving north to south, just a bunch of cumulus and a bunch of little streets,
Interesting.
and that's streaming in moisture. What do you call it, the wind sort of lines them up.
So vertical motion cloud formation, this can get pretty dense. Really all you need to know is that the atmosphere will cool down as you go up, roughly 2 degrees per 1,000 feet. If it cools down any faster, Celsius, sorry, yeah. If it cools down any faster than that, you have the potential for an unstable atmosphere. If it stays the same, or if it cools down at 1 degree Celsius per 1,000 feet, or if it gets warmer as you go up, that's a stable atmosphere, and not much goes on in that case. Air will decrease in temperature as you go up based on whether it's saturated or not. So water holds its temperature, so if an air mass is saturated, it'll decrease at about 2 degrees per 1,000 feet, and it's either like 1.5 to 3, something like that, 1.2 to 3. Whereas a dry air mass will decrease at 3 degrees per 1,000 feet until it becomes saturated, and then at that point it'll decrease at 2 degrees per 1,000 feet. So you can get really complicated with how you look at this. The dew point decreases at 0.5 degrees per 1,000 feet. So knowing that, if you know the temperature and the dew point spread, the difference between those, you can divide it by 2.5, multiply it by 1,000, and you should get your cloud bases from the surface. And that might be on your written test too, but 2.5 degrees Celsius is how they converge, because you have your dry adiabatic collapse rate of 3 degrees, and your dew point decreases at about 0.5 degrees per 1,000 feet as you go up. So again, you could get really complicated with this, but that's kind of in the nutshell what we're looking at here. Interesting thing to note as well is that a descending parcel of air, once you get it lifted all the way up here, you have your big cloud, you get it all the way up here. Once you start making it go back down, it'll immediately warm up at 3 degrees per 1,000 feet. And now that it's lost all its moisture, it'll end up back down at the surface quite a bit warmer than when you started to lift it. So it's kind of weird. But if you lift a parcel of air up this high, and then make it go all the way back down after it's become saturated and lost a lot of water, it's going to end up warmer than what you had in the first place. Which kind of makes sense, I guess, because warm air can hold more water. And that's kind of a good graph with unsaturated versus saturated lapse rates. A couple different ways to lift an air mass is graphically over a mountain, or frictional with a low pressure system. You have low pressure is just mostly rising air, high pressure is descending air. So if someone asks you what's the difference between high and low pressure, well, low pressure is converging ascending air, makes for exciting times. Right, high pressure is descending diverging air. And since it's descending, it's warming up, it's compressing, it's losing water, basically. Well, it's not losing water, but it's just the capability to hold water is becoming more of a thing. Frontal lift, buoyancy. If you have a warm air parcel, it'll want to go up because it's less dense. It's how hot air balloons work, it's also how thunderstorms work. So if you think of a thunderstorm kind of like a hot air balloon, that's kind of how it works. Here, we're getting closer to my favorite part. Atmospheric stability. Again, this can get really complicated, but we've kind of already talked about, you know, if the lapse rate is more than 2 degrees Celsius per 1,000 feet, you have the ability for an air mass to be very unstable. If you have a temperature inversion, or if the temperature increases as you go up, then you have a very stable atmosphere. Kind of in this case, I think. I can't remember if this stays the same or not. But we'll kind of skip through all that because we already talked about this. There's neutral stability, which is if you lift an air mass up and it just stays there. And then there's absolute instability, which is if the air mass just wants to keep going up and up and up. And there's conditional instability, which is if you have to lift a parcel of air up before it starts to rise by itself. And the whole reason why an air mass or air parcel wants to rise is because it cannot cool down fast enough to match the surrounding air. Does that make sense? So if you have, especially true if you have water inside that parcel of air, it won't cool down as fast. And that's really the theory behind a thunderstorm. Here's a couple of stability types: inversion, isothermal, moist, adiabatic lapse rate, dry, super adiabatic lapse rate. So this is really unstable. This is what would make your thunderstorms go off. We'll kind of skip through that because this can get really complicated, but you won't be asked about really complicated questions on your written test, and definitely not your practical test. They just want you to have a good basic knowledge. Clouds. Try to wrap it up quick here. Clouds. The only thing you really need to know about clouds is that there's 4 types of clouds. There are high clouds, there's low clouds, there's middle clouds, and clouds with extensive vertical development. It sounds like a trick question, but it's not. When they ask you what are the 4 types of clouds, and they give you altocumulus and stratus, and they're looking for high, low, middle, and clouds with extensive vertical development. Those are kind of the main 4 types of clouds. And of course, you also have cirriform, which is usually higher. You have nimbus, which is raining clouds. You have cumuliform, which is unstable thunderstorm type of clouds. But you could have fair weather cumulus, so it's kind of the same principle, just without the thunderstorm rain part. And then stratiform, which is just a flat, stable layer of clouds. Cloud levels, again, you can get kind of complicated with those, but you can just kind of guess if you need to. On the written test, high clouds, obviously, they're at high altitudes, and low clouds are kind of at low altitudes, and middle clouds are at middle altitudes. They also have a tendency to kind of combine cloud types. They have cirrocumulus, cirrostratus, cirrus, altostratus, which is kind of middle, right? Your altocumulus. Cumulus just kind of looks bumpy, and usually cumulus clouds have more water droplets in them, so you have more icing potential if they're higher. Whereas like a cirrus cloud is mostly made out of ice, unless it's called a cirrocumulus cloud, and then it has some water droplets in it. Standing lenticular clouds are kind of cool. You'll see this over a mountain, or you'll see this, sometimes you'll get them around here, you'll see just a lens type of looking cloud. Basically the principle behind this is that you have a stable layer of air moving this way, and then it'll hit an updraft, it'll go up, it'll reach its dew point, then it'll go back down, and nothing happens after that. In this case, I think it's going across the mountain, lifts up, comes back down, comes up again, because now it's got that sine wave action into it. Yeah. So it's kind of disrupted, but it's stable air is the main thing.
You want to fly next to them.
You don't want to fly next to them.
Typically, it's really windy too. You see them here in the windy
Yeah.
days.
Yep. Different types of clouds, I like to combine names again. There's a fair weather cumulus cloud. Here's a towering cumulus. The ones I like. Never mind. Cumulonimbus without an anvil, and cumulonimbus with an anvil. Here's that tropopause layer right here at the top. Sometimes you'll see, if it's a really impressive thunderstorm, you'll see an overshooting top, which is, just kind of gets enough momentum going up there, it kind of blows up at the top and then it flattens out. Again, that's, kind of where where the air stops cooling off as you go up, and it stays about the same temperature, and then it starts cooling back up again in the stratosphere. Yeah, thank you. It's been a while. Yeah. Yep. Precipitation is also pretty easy. There's not a whole lot to glean for these purposes here. That's just kind of how a water droplet forms. If you have precipitation falling from a warm layer into a cold layer, you could get the potential for icing. We aren't really going to be dealing with that this time of year, so I'll come back in the fall for our icing seminar. And then, obstructions to visibility. Types of fog. I will ask you about this types of fog. We talked about radiation fog. You kind of know what that is already. It's just when the surface of the land cools at night. Light winds, maybe a high moisture content, but it's kind of a nighttime thing that happens. Radiating that heat off of the surface into the atmosphere. Yep. So that's the principle behind radiation fog. Usually it'll burn off pretty quick, unless it's really determined, but generally around here it burns off. Here's that advection fog around San Francisco. That will not burn off very quick. That's just there to stay until that whole air mass moves somewhere else. Because it's picked up a lot of heat over the ocean. It's picked up a lot of moisture over the ocean. Now it's in San Francisco where it's not as hot. So it cools down to the dew point and you get fog. And there goes your day of flying. God, we don't live in San Francisco. But of course we have wind around here, so it's all kind of a trade-off.
Unless you're doing your IFR.
So during your IFR, then it's excellent, yeah. Yep. Upslope fog is just a layer of wind or a layer of air moving up a slope, forms a dew point. You could call that a cloud, I guess, right? But I guess it's close to the surface, so they call it fog. Frontal fog, that's kind of an interesting one. I also call that precipitation fog. Some people call that precipitation fog. Your textbook might, but that'll happen when you have a warm layer of air dropping precip into a colder layer of air, and as it does that, it will cool off the colder layer of air even further to the point where as it evaporates, to the point where it forms fog. Due to that latent heat transfer, if you have water droplets that are evaporating, you have to send the heat somewhere, and have to go into the water droplets to make them evaporate. So that's an example of latent heat transfer in fog.
Hailstorms too.
Yeah. Log snow, dust storm, sandstorm. We don't really get those around here. Abu. Yeah, I guess it does in Arizona.
Yeah.
I guess that's more of a thing when you're flying down there. You do not want to fly through one of these. Low ceiling, mountain obscuration, simple stuff. Turbulence. A couple different types of turbulence. You have convective turbulence, which is just associated with a thunderstorm or something like that, or an unstable atmosphere like a thermal or something like that. That'd be convective turbulence. Let's see, there's your thermals. Mechanical turbulence. Somebody built a giant building off of final to runway 16. And now every time you fly by that building, you get a significant sinker. If you've ever flown by that thing, and it'll surprise you if you have a lot of headwind, especially coming into land. It'll wake you up because you'll be at eye level at the bottom of the roof if you aren't watching out. And yeah, it's significant. But that's an example of mechanical turbulence, kind of that wind flowing over the top and then kind of down afterwards, and that spiraling effect. Mostly downdraft, I guess, in the case of our handy wedding shop building that they put up in front of the runway. Mountain waves, another example of kind of mechanical turbulence just on a really big scale. Don't really deal with this around here because we don't have mountains. But you'll come across this in your written or in your study for the written test. You have your cap cloud, and then your lenticular clouds and your rotor clouds underneath that. Usually downdrafts on the leeward side of the mountain. So if you're flying on this side, and you want to cross over this ridge, you're having a great time. Your airplane's performing well, and you're climbing nice, and then you get to this side, and you might not be able to hold altitude after that. In fact, they've had instances where, you take Piper Cub up to 12,000 because it'll just climb up there in that updraft, and then it'll crash on this side of the peak because it's a downdraft and it just can't maintain altitude at 11,000, let alone out climb a mountain wave like that. So that's kind of the things to watch out for. Things to be aware of if you ever want to fly in the mountainous areas. Just grab an instructor in the area who knows what the deal is, and head up for a little bit. Good experience. My uncle's done that, yeah. And I would like to do that at some point as well, probably before I move to Memphis, so it's not quite as much of a flight. Wind shear turbulence, just 2 layers of wind going different directions. Obviously results in turbulence. You can also get turbulence with an inversion. This will also be a written test. You have like winds 5 knots or something like that at the surface, and then inversion aloft. Clear air turbulence, usually really high altitude, so won't worry about that. And we're going to skip the chapter on icing because it's for the fall seminar.
That's
Yeah.
the next one.
Yeah. Let's see. Thunderstorms. The grand finale, and then we'll be done. So thunderstorms, we already talked about kind of how a thunderstorm forms, but 3 things you need for a thunderstorm are unstable air, talk about what that is, you need moisture, and a lifting force, right? So if you have a front, or if you have a mountain, or if you have a thermal, some way to get the thing to lift past the lifting condensation point, and then it'll just explode on its own, and there you have a thunderstorm. There's kind of 3 main parts to a thunderstorm life cycle. Here's your cumulus stage, and that's kind of the especially at middle afternoon, you're starting to get these clouds, and you really don't know what's up at that point because there aren't any other big clouds like this to tell you that this is going to turn into this in the next 20 minutes.
They grow up so fast.
Yeah, they do. But you won't see any radar coming off of this one. So if you have some sort of weather radar from ATC or in your cockpit or on your iPad, and you think, oh, doesn't look too bad, no radar, right? And then 20 minutes later you get this. So it's just one of those things you have to be careful of. Thunderstorms especially, they look fun on your iPad, but when you're gonna have to look more for how fast the atmosphere is cooling down per 1,000 feet. ForeFlight has a handy warning that comes up, and it'll tell you if the atmosphere is potentially unstable, and that's a good heads up that hey, these clouds might turn into something more than just nice little cumulus clouds to fly around. But then, of course, you have your dissipating stage after that, mostly just downdrafts at that point, and rain and possibly hail and stuff like that. And again, it's interesting, there aren't any clouds right here because it's already lost all its moisture. So from here on down, all it's doing is warming up and becoming drier. It's already lost all the hail and the rain and the moisture off of the water vapor that it used to have right down here. Kind of how it propagates. You have a couple different types. You have multi-cell cluster thunderstorms. You have the line thunderstorms, and then there are your single supercell thunderstorms. We kind of get a mix around here. We don't really have any supercell thunderstorms, I'd say, around here.
We do,
Okay, really rarely, I would say.
they're rare.
We had a couple of them, I think, a couple weeks ago. It was weird. We had like this giant purple thing in Grand Forks, and then nothing for hundreds of miles around, and this giant purple thing in Denver, nothing for hundreds of miles around, this giant purple thing down in Texas or something like that.
Supercells are usually
They go it along.
95% of the tornado,
Yeah.
the damaging tornadoes.
Okay.
You can have tornadoes come from frontal storms, but they're usually pretty weak.
But yeah, and then you have the line thunderstorms would be just kind of the thunderstorms arranged in a line, and usually anything else is kind of just associated with thermals, so they're just kind of pop up wherever. But yeah, kind of how it propagates. is weird. You'll have, everything's kind of moving this direction, but after it, it'll build up to this phase and then it'll dissipate. In another 10 minutes, you'll have another one propagate behind it. And it'll look nice and calm and not very threatening, but this will turn into this in another 10 minutes. So just be aware of that. There was one flight we were starting up, and there was nothing on the radar. There was this little tiny green speck out about 15 miles south of us, and there were some other thunderstorms in the area, so I was kind of on my guard with it, but it was just this little tiny green speck on the radar. We did our run up, and this giant clap of thunder. You hear that? I don't think it was even thunder. Even it was just a flash of lightning. So I don't know if I was seeing things.
It was just
or what. Yeah, I don't think it was even thunder.
Backfire.
So, yeah, could have been back. Something off of the engine run up or something like that. So I didn't know if I was seeing things. We headed out to we started taxiing out to the runway, and then a big giant clap of thunder and lightning, and shoot, well, we'll just taxi back then. Put the airplane in the hangar. As we were pushing the plane into the hangar, we were getting hail, because that's how fast that little tiny green speck had.
So was that must have been 5437 Fox
Yeah.
then? All the planes-
Well, that wasn't that wasn't that incident, but as we pushed the thing in the hangar, it just went no rain at all. It just went straight to hail. So
So that happened in minutes?
about 5 minutes.
5 minutes? Oh, how interesting.
Yep. So, as you can imagine, hazards off of thunderstorms include lightning, adverse wind, downbursts. You'll hear a lot of talk about microbursts, but just huge downbursts in general. You'll get a gust front off of the downburst. It'll pick up a lot of dust and stuff like that. So if you see this big black storm cloud out here and then dust in front of it, just land the plane right now, because it'll get exciting. Or tie the plane down or get it into a hangar, because it'll, I was showing some pictures earlier of pre-flighting out on the FedEx ramp in Sioux Falls, and that was what I was experiencing. That's kind of your downburst life cycle there. Landing the microburst, you'll get a lot of, just don't do it, really. That's kind of the moral of the story. Just don't fly close enough to a thunderstorm when you're landing that you might have a microburst. Yeah, but these can, I can't remember what exact, it's a couple thousand feet per minute down that you could get in these downdrafts. And I did some math, and it would be about, you got a full-fledged microburst in the traffic pattern, and then went full throttle, and one of our warriors would take you about 12 seconds to hit the ground for pattern altitude, and you could go full power and just pitch the thing up and sit there, and you would still hit the ground 12 seconds.
Yeah, so we get headwinds and then tailwind all of a sudden.
Yeah, yep.
So what happened, I think there was American and Dallas Airlines.
It says MD-11 or something like that.
Yeah,
Yeah.
this caused, all of a sudden now we have radars around airports, except for here we put right at the.
Yeah, wind shear alert systems and all that.
Yeah.
Yeah. So if you hear wind shear alerts, people take those pretty seriously, but around here we have so much wind that it'll kick those things off pretty similarly. So you kind of have to take it with a grain of salt. If it's a clear day, caution low level wind shear on the ATIS, and when the tower clears to land, just means that it's really windy. You might want to consider the wind again. Take a look at that wind value again. But if it's a thunderstorm, then you really have to be watchful, because if it's, we're just turn around and go somewhere else, because once that gust front hits and you have potentials for microbursts, you could be seeing a microburst kicking off one of those sensors and actually setting off a wind shear alert. So that's kind of the moral there. And as Thomas was saying, you get a headwind here, good climb performance, so you pull your power back and start descending fast, and then you get right here, and then you start getting a downdraft and tailwind, so you go full power, but it's usually too late at that point. Happened to the 11, and the whole thing just
Hit a fuel
crashed.
farm.
Hit a fuel farm, yeah.
It's like the first time we did.
Yeah.
Yeah. rapid altimeter changes, static electricity, tornadoes, all results of a thunderstorm.
On those microbursts, there's really nothing visible that you can see.
You can see the dust ring around it. If you can catch it before it becomes, well, if you can see it after it hits the ground, you'll see a dust ring around it. And really, if you have a thunderstorm and you see dust on the ground, and it's surprising how much dust you'll be able to see. But you'll just have to watch for it. If you see dust, turn the plane around and go back.
It's typically associated with, you can see rain.
Yeah, the
But
other
you
thing
just-
too.
You should just assume
yeah,
that there's going to be a downburst someplace around the thunderstorm.
if there's a rain shaft or something like that, usually has some sort of downdraft associated with that. There's a really good video. Just Google wet microburst, and a wet microburst is just a microburst with rain in it. But they have some pretty cool videos of yeah, just a big bucket of just a huge slew of rain and hitting the ground, and it blew up into like an explosion type of thing. But, yeah, you'll be able to see it usually, and if you can't see it, you should have other signs like the pictures I was showing you, the big black. If you see black, don't go into it. Don't go into that shelf cloud because it will be exciting, whether you see dust or not. So, and that kind of concludes everything I wanted to cover. Thanks again for coming. It's been a lot of Yes, that was the other thing I want to bring up. Mark and I were talking, we kind of want to do this on a monthly basis. So the EAA is starting to do its pancake breakfast again on Saturdays at 8 a.m. And we'd like to do something like this at 10:30, 10-ish, something like that after the pancake breakfast. So the whole morning of fun. But that's kind of what it's nothing official yet. So just watch your emails. We'll get third Saturday every month. Yep. So this next third Saturday. So next week we won't do anything because we did this. But that is something we want to do. So it's
Now,
in the works.
will the seminars always be weather, or will it be different topics?
It'll be different topics like instrument approach charts, or something more exciting like medical. Yeah. Yep. Yeah, you and Thomas both. Yeah, you and Thomas both. So yeah.
Which doctors to go to and which ones not to go to.
Yeah, yeah.
Should never go to A, the hangover. Can you get wings credit for this?
You can. I think Mark's working on it.
Good.
I think for this one, he said, I don't know if he's able to get it to work for this one, but that is something he wants to do, as well as to give you a little wings credit for coming. So, and in that case, you can, I don't know how much you can apply to a flight review, but you can opt out of the ground list and on flight review if you so desire. And if your instructors are cool with that. Still a lot of things good things you can learn on the flight review ground list. But thanks for coming, Brian. We'll see ya.
Thanks, Will.
But yeah, you can theoretically skip the ground list. So.
Well, what was the name of, what was it, just the weather?